I have to apply natural log to this side and natural log to this side. The left-hand side is clear. Can anyone tell us what to do with this? The natural log of a product of three quantities, 1, 2, 3. Is there any log rule, rule of the natural log or logs in general, any log, that will allow us to simplify this a little bit before we differentiate? We reviewed the logs of the rules of logs. Anyone remembers?
I want to say you can break each one apart.
Yes. How?
To make it natural log square root of x, natural log square root of e to x squared minus x. Then, but I'm trying to remember if it's plus or times in between there. I want to say it's times.
It cannot be times, it's plus. Very good. So natural log of the square root of x plus natural log of e to x squared minus x plus natural log of x plus 1 to 2/3. Excellent. Thank you. So let's write the rule again. Log of x times y is log of x plus log of y. This is the rule that we just applied. If it's log of x over y is the same with minus. Log x, log y. And the last property is, that's the second one, log of x raised to b power. So this is b times log x. In any base. I didn't put a base, I just said it's a common log, but it can be any base. They all function in the same way. So the product rule, the quotient rule, and the power rule. So we use the product rule. Excellent. Now I have to use the power rule because all these have powers to further simplify. So how do I continue? Can anyone help? I have natural log on the left-hand side. What power goes in front here?
1/2.
Excellent. Natural log x plus. When I put this power in front, what happens to natural log e?
It turns into 1.
Excellent. X squared minus x plus, I put the power in front, natural log x plus 1. We do not have any rule for natural log of a sum. Don't touch that. This is the maximum we can do. So at this point, we will differentiate.
You don't have to subtract the exponent and the x plus 1 minus 1?
I'm not sure I understand which one.
When you move the 2/3 over to the front, when you do the 2/3 minus
I'm
1,
not differentiating. I'm only using this power rule. Right? I'm not differentiating. After I finished, now I will differentiate. So from this step till this step without the symbol of differentiation, I didn't do anything. I just did algebra. So I applied, for this, I applied natural log x to b, so I put b in front. I did not differentiate. This is just algebra. I use this rule. Is that okay? Are you with me? Is this okay?
Yes.
Okay, perfect. So now we are differentiating both sides. Can anyone give us the left-hand side?
Is it 1 over y?
Y is a function.
Times
the y prime?
Yes, dy over dx or y prime. I recommend this notation, please. Do not use y prime. It could get confusing and you may omit the prime. Who knows? I highly recommend this notation for implicit differentiation. It's up to you. I will accept it. You can put f prime, you can put whatever else you want, I'll accept it. But if anything goes wrong and you drop the symbol and you don't solve for it, then okay. So then we're 1/2. I differentiate this. What do I get?
1/x.
Very good. I differentiate this.
2x.
Good. I differentiate this.
1.
Very good. I differentiate this.
1 over x plus 1.
Times the inner function prime. How much?
1.
That's it. Now I'm solving for dy over dx. So I have to multiply by y, but I will multiply by this ugly thing because that's what y is all about. So the square root of x e to x squared minus x and x plus 1 to 2/3 times this whole thing. 1 over 2x plus 2x minus 1. No surprise, I ran out of room, right? Plus 2 over 3x plus 1. Look, I managed to squeeze it in. This is it. Good question. Do we need to see another function raised to another function? Prime. I think we should do one more. Let's say, I don't know, 53?
Can you do 54?
54. Okay, so we have y equals sine x raised to natural log x. Good. Okay, so this is a function raised to another function, no rule. No differentiation rule, that's what I meant, but we have a rule, which is logarithmic differentiation. So we apply natural log to both sides. Natural log y, remember the power goes in front, natural log x times natural log of sine x. So I applied natural log to both sides. So natural log, the power goes in front, times natural log sine x. Only now I can differentiate. So let's see what we get. The left-hand side, you already told me several times, 1 over y times dy over dx. But now here, this is a product. I have the feeling that we did this problem last time, but maybe not. So natural log prime, 1 over x times the second function plus natural log x times the second function prime, 1 over sine x times the inner function prime, which is cosine x. So 1 over y dy over dx equals 1 over x natural log sine x plus cosine over sine is cotangent, natural log x times cotangent x. All I have to do is what I did here, multiply both sides by y. But I will not multiply by y because I have to multiply by sine raised to natural log x. And that's it. That's final. So dy over dx equals sine x raised to natural log x, and this whole thing in brackets. 1 over x natural log sine x plus natural log x cotangent x. Yay, I managed to fit it in. Any questions? I like to jump to any questions, please. I'm not going to rush you. I don't want to rush you. I just need to get to 311 when you're ready. Any questions on this? Any questions? Anyone? Is this okay? Please talk to me, anyone?
Sorry, I just keep looking at it. It feels like in other problems we had to break it down further, and this seems like really large answers. So just trying to wrap my head around it.
Okay. Anything else? Okay, so we have what is called, I promise you this is the last function, a group of functions, hyperbolic functions. Hyperbolic functions are exponential functions, basically, at the core. And we're going to look at 3 of them. There are 6. Let me list them first. Hyperbolic sine, hyperbolic cosine, hyperbolic tangent. And you can say, you're saying that they're exponential functions, but I see sine, cosine, and tangent because of their relationships among them. That's why. And the other ones, of course, they are cotangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. These I'm not really interested in. They're fine, nothing wrong with them, but I just want the basics for the first 3 that are widely used. So they are, as I said, exponential functions. And then if you ask, again, why, okay, if they're exponential functions, why this? Because they have relationships similar to the trig functions, that's why. So here it is, e to the x minus e to negative x divided by 2. And the second one, the cosine, is the same but with plus. So e to the x plus e to negative x divided by 2. And this one obviously is hyperbolic sine over hyperbolic cosine. So since I don't have enough room there, I'm going to just put an arrow. So this is hyperbolic sine, hyperbolic cosine. And of course, the relationships here are the same. This is hyperbolic cosine over sine. This is 1 over cosine hyperbolic, and so on and so forth. And they have similar trigonometric identities among them with the ones that we know from trig functions. Okay, so why do we need these? Don't we have enough functions? Oh, well, no. So let me just give you an example of an application of this. So one application of hyperbolic cosine is, you've seen this, when we've seen this everywhere on the road, 2, I don't know, telephone poles, or not anymore, but for cable, or I meant to say power lines, you will see something like this, right? So no power line is completely horizontal. Well, how did they determine this for the best optimal and weight, etc., with using a hyperbolic cosine function? So the graph of the hyperbolic cosine function is something like this. It looks like similar to a quadratic function. And the same thing, so at 1, something like this. So this is hyperbolic cosine. Okay. Hyperbolic sine, again, it's similar to a sine function, but it's defined everywhere. These functions are defined everywhere and take values everywhere, except cosine, right? Hyperbolic cosine from 1 to infinity for the range. The other application is, I have not been to St. Louis, but there is what they call the arch of St. Louis. The arch of St. Louis is a hyperbolic cosine function. Okay, so they use a hyperbolic cosine to build the arch that they have at the entrance to, I think, to St. Louis. I'm not sure. I have not visited St. Louis. Okay, so what about their derivatives? And that's all I want. Okay, and then we'll look at problems. So again, we're going to look at these first 3. I don't need inverse hyperbolic functions. Okay, if we are asked to do any of that, we're going to look at the table. But I just want the basics. So hyperbolic sine prime is hyperbolic cosine, as you probably guessed. And what do you think a hyperbolic cosine prime would be?
Negative sine.
Correct, but this time is just positive.
Okay.
Yep, awesome. That's exactly what I was expecting you to say. And the hyperbolic tangent, of course, is hyperbolic secant squared. So very similar to the trig functions, although they're not trig functions. But again, we use this prefix only because their relationships among themselves are similar to those of trig functions. Okay, so that's all I want. And that's all we need for that assignment. And moving forward,